Hello everyone. In this video, we will learn how to write rational function with some good conditions that we will get on that later as sums of partial fractions. And this I will start through an example and then develop the theory, and you will see at the end everything is as simple as the first example that we did. Okay, so here someone told us that this function 5x plus 4 over x squared plus 2x is sum of two partial fractions. The partial fractions which have linear terms in the denominator. In other words, this can be written as a1x plus b1 and then another a2x plus b2 in the numerator. Well, definitely there's partial fractions are defined like that. Yes, for the linear denominator, we have to put constant. Now I have to find what are the coefficients and so on. But for a second, just think about this part, that if I want to simplify the right-hand side, the first thing I should do is that find the common denominator. And common denominator here means that you multiply the denominator and then do some work there. But look at the left-hand side. Left-hand side's denominator is degree 2. Right-hand side denominator, if I multiply, I will get degree 2. What does this say? This says that basically this guy here is decomposition of that one. So in other words, a1x plus b1 times a2x plus b2 is the decomposition of x squared plus 2x to its factors. How does this going to help us? Well, this is easy function to factor. I can factor out x. And well, this, voila, you see, on the right-hand side, I have two factors. On the left-hand side, I have two factors. These factors must be the same. Otherwise, this doesn't make sense, this equality. So what I have shown here for you is that, well, the denominator of those partial fractions must be the factors of the denominator of the rational function. Okay, so then I will start the question again. So now that I know what are the denominator of the partial fractions, I will write this. And well, this time I don't need to put a x plus b thing. So here I would just put those two. There is no other choice here. Those must be equal to that. And then, well, we know that now the numerators must be some numbers, but we don't know what are those. So we have to try to find that. Okay. As we started, let's just continue the way we started. So I want to simplify both sides, but I will start with the right-hand side, find the common denominator. Once it helped us to find what are the denominators of these partial fractions, now I want to use them for the numerator. So here this will be x plus 2 plus a 2x. Very nice. Now I look at these guys. Right-hand side and left-hand side have the same denominator. I can cancel them. And then as a result, the left-hand side must be equal as a polynomial to the right-hand side. Let me simplify right-hand side. So put x's together, so that way we will get a1 plus a2 times x and 2a1. Now, the problem is that we have two polynomials, one on the left-hand side, one on the right-hand side, and these are equal. It's very easy to show that two polynomials are equal if and only if their coefficient, corresponding coefficient. So on the left hand side, the coefficient of x must be equal to coefficient of x on the right hand side, and the coefficient of the constant term on the right hand side must be equal to constant term on the right hand side. So this way, then we have an equation. So we have setting corresponding equations, corresponding coefficients equal. What do we get? We find that 5 must be equal to a1 plus a2, and 4 must be equal to 2a1. We find an equation or set of equations for a1 and a2. Well, I can solve the second one and find a1, plug it into a2, so it will be 5 equals to 2 plus a2. From there, we see that a2 must be equal to 3. We have found not only the denominators, but also the numerators of the partial fractions. This guy, 5x plus 4 over x squared plus 2x, must be equal to 2 over x, yes, a1 over x, and a2, which is 3 over x plus 2. We found two partial fractions. When we add them, we get the the rational function that we started with. And here, well, there are some things that we will talk about it in a minute or so. But just for a moment, note that it was important for us to see that the denominator of the rational function decomposes to just linear without any repetition factors. And that would be something we will take with us until the end of this video. Okay, let's do another example. Okay, let me delete this first. So here the question asks for integral. Why integral is related? Look, if someone was asked me to find the integral of this rational function, that wouldn't be easy. But the right hand side, the integrals are easy. I know how to integrate partial fractions. That's why partial fraction decomposition is important for us, and it's a technique for integration. So here, then we want to write x minus 3 over x squared plus 5x as sum of partial fractions. So we start as before. We first factor the denominator. Those factors are exactly what we will use in the denominator of our partial fractions. Again, important thing here is that these are linear without any repetition. So that means that x minus 3 over x squared plus 5x must be equal to sum of two partial fractions, with one with denominator x, the other one x plus 1. I will put the numerators, one as a, the other one as b. These are constants that we have to find, yes? Now, I go ahead and find the common denominator there. So this will be a times x plus 5 plus b times x. Since the denominators are the same, so we can conclude that the numerators must be equal to each other. But the numerator of the right hand side, I can write it as a plus b, put x's together, plus 5a. Now, the two polynomials are the same. That means that they have same corresponding coefficients. Here, the constant is -3, that's 5a, and the other hand is the coefficient of x is 1, and coefficient of x is a plus b. So from there, then we can conclude that a plus b must be equal to 1. The coefficient of x is 1. And 5a must be equal to negative 3. From here, I can find a right away. What will happen for this one? Negative 3 over 5 plus b must be equal to 1. Then that means that b is equal to 1 plus 3 over 5, which is 8 over 5. We found a, we found b, and our fraction now can be written as a, which is negative 3 over 5. It's a constant over x plus 8 over 5, and this is x plus 5. How is this going to help us to integrate? Well, if I integrate both sides, on the right hand side I will have two integrals of partial fractions, which I already know how to integrate. So that will negative 3 over 5 ln of absolute value of x plus 8 over 5 ln of x plus 5 and plus c. So you see, when I decompose it or write the sums of partial fractions, the rest is just easy because we know how to integrate partial fractions. Let's do one more example here. This example has another point that I should bring it up here before we move on. And that is that here the numerator, the degree of the numerator is equal to degree of the denominator. Always, if your denominator has less degree than your numerator, you must start with long division. So in this case, we have x squared here, x squared minus 4x plus 3 there. So I will have only 1. And then we subtract here. This will cancel that. Everything else will be 4x plus 3. That means that x squared over x squared minus 4x plus 3 must be equal to sx, that's the coefficient, which is just 1, plus rx remainder over qx. And you see there's this polynomial, well in this case constant polynomial, and there's another fraction which has lower degree in the numerator than the denominator. Now we can decompose, we can write 4x plus 3 over x squared minus 4x plus 3 as sums of partial fractions. And that's true always, fractions. What would be the starting point? Look at the denominator. Factor the denominator. So here I have two things. When you add up, you get negative 4. When you multiply, you get 3. So this is x minus 3, x minus 1. So that means that our fractions, partial fractions, one is going to have x minus 1, the other one x minus 3 in the denominator. And these are going to add up to x squared minus 4x plus 3. Don't confuse it with this one. We are now working with this guy here. The power of the degree of the numerator must be less than the degree of the denominator. Here I'm going to have two constants. So I will have this guys, and then This will be x minus 1 times x minus 3. The denominators are the same, so I can cancel. As a result, we can see that 4x plus 3 is equal to a plus b. I'm putting x's together and then constants together. Minus 3a and minus b. So now the coefficient of x must be equal to coefficient of x. Coefficient of the constant must be equal to constant. So from there, you see that we find a system of linear equations where a plus b is equal to 4 and minus 3x minus b must be equal to 3. We have to solve this. One of the easy ways to solve is that here, if I add these two equations, b and negative b, they will cancel each other. As a result, I will get negative 2. Oops, why do I have x there? It should not be 3a. So if we do that, this will negative 2a is equal to 7. That means that a must be equal to 7, negative 7 over 2. If I have that, I know that if I add it to b, then must be 7. So this way, b is going to be 4 plus 7 over 2, which is 15 over 2. So let me then go back to our work here. Now I can't say that I know how to write that piece as sums of two partial fractions. Just remember that there's a 1 there plus there is this x minus 1 and there's x minus 3. Yes. And in the numerator for x minus 1 we have a, which I now know is negative 7 over 2. For b we have 15 over 2. Yeah. And that way we are good to go, because if you're interested in integral of x squared over x squared minus 4x plus 3, we first write it as 1 minus 7 over 2, 1 over x minus 1, and 15 over 2 integral of 1 over x minus 3 dx. And these are partial fractions, and I'm assuming that you know how to deal with those guys. And 15 over 2 ln of x minus 3, and I will write plus c, don't forget that. And this way we have done all the steps required. Let me just before we leave, we do an overview here. So you want to write a rational function f over g as partial sums of partial fractions, or what we call partial fraction decomposition. You have to check two things. First is that the degree of the numerator must be less than the degree of the denominator. If not, you have to use long division. So if not, use long division. And then we decompose G. And if the decomposition is product of linear terms without any power. So these are product of linear one. For each one of these ones, each one is supposed to be the denominator of one of partial fractions. So that way we know that f over g must be sums of these kind of partial fractions. We already know what are the denominators, but we are looking for the numerators. How do we find it? We find the common denominator and then simplify both sides. Both sides will have numerators and denominators. Denominators are the same, so we have to set the numerators equal to each other, and then find equations out of two polynomials being equal implies that their coefficients must be equal. And then we solve it for those coefficients and find a, b, and so on. Okay. So that was a story about how to write, find the partial fraction decomposition of a rational function which has a denominator that decomposes to distinct linear factors.